Thanks a lot. All right, so I'd like to talk about some work we've been doing in the Emerging Products and Technology group at Autodesk in the Cloud Platforms division. So a group of us in the EP&T division, we've been looking at this problem of a design graph. What I'd like to do here is present some of our recent work using Apache Spark to run the pipeline that actually builds this graph. So very quickly, this design graph is our knowledge graph in the context of design that we foresee enabling very powerful navigate, explore, and discover workflows for our designer customers to find the information that they need to get their design jobs done. All right, so before jumping into the specifics of the design graph and how we're using Spark, let me just very quickly give you some background on Autodesk itself. All right, so Autodesk is a company, it's been around for a while. We build design software and services to help many millions of designers around the world to imagine, design, and create a better world. All right, so you may be familiar with our flagship product, AutoCAD, but we also provide design software for other markets such as in manufacturing, architecture, infrastructure, to consumer, and even media and entertainment spaces. Right? And in fact, more recently, we've started embracing some hardware as well with our 3D printer offerings. All right, so as with most modern software companies, Autodesk is embracing the cloud with services for its various web, mobile, and desktop applications. All right, so with this added value, our customers are now pushing considerable amounts of design data into our cloud storage offerings. All right, so we in the EP&T group have been exploring this idea of looking at this vast aggregated design data set and learning models of designs that we can use to inform our customers. All right, so for example, maybe helping them find the information that they need to get their design task done. All right, rather than perhaps wasting a lot of time trying to find their part files or their design files that they need as reference for their job in their local directories or on the remote repositories, or worse yet, maybe just giving up entirely and starting every design task from scratch, which is unfortunately not an uncommon problem. Right? Furthermore, we're aiming through this design understanding to be able to surface some problems in a design before it, say, hits the factory floor. All right? A flaw in maybe some design of a part may bring a production line down, right, which can cost considerable dollars as you have to retool to deal with that mistake. All right? Some other requests that have come up are things like surfacing cost savings by consolidating vendors as you're generating your bill of materials. All right, so no big surprise here. A graph well represents these kinds of relationships between the design bits that surface this kind of information. All right, so much like how Google uses the knowledge graph to augment search or enhance search results, or how Facebook uses the social graph to surface updates about your friends and acquaintances, we envision using the design graph as a way to surface important information for our customers to really help them get their jobs done. All right, so we know that we want to build this design graph. The question becomes, well, where do you start? You know, do you link people together? Do you look at designers, contractors, machinists, makers, and link them up? Or do you go to the company level, connect up companies and vendors, buyers and suppliers? Or maybe you go to the project level looking at things like specification documents, perhaps collaboration streams, or go to the design file level, or maybe go all the way into the bedrock, right, and start mining the data that's embedded in the design files themselves. Now, from a customer point of view, they want all of that, right? They want access to all that kind of information and have those things be surfaced to them, right? So that doesn't really answer the question of where to start. Now, in terms of what we're collecting, we are collecting at all those levels, all right? But you know, we're not a LinkedIn. We don't have vast amounts of people data or company data. What we have a lot of is really at that bedrock level, all right? The designs and the embedded information in those designs, all right? For us, then, it makes the most sense to start at that level, all right? Start with the designs and the embedded parts, learn those implicit relationships, build that strong foundation of a graph, and then start to add in those other layers and leverage those learned relationships as we add those other parts in. Okay, so fortunately, as design has been moving into 3D, right? It means for us to extract out some of the information there. It's become much more easier. And this just kind of falls out in terms of how users work with parts and models as they design in our design softwares, right? So that's good news. Let's take a little bit closer look at parts and designs, right? If we sort of flip it around and look at all the designs that parts can be embedded in, right, we find that parts are actually a really nice signal for classifying designs, right? So for example, toilets and doors are great indicators of building or house designs. Another example would be character rigs, all right? Skeleton structures are great indicators of finding CG characters that might be used in computer games or in special effects. Right? So this leads us, if you will, to a guiding principle that parts in designs are very much like words in text documents. Right? So this gives us some tools from the natural language processing playbook that we can apply to learning the implicit relationships that we want for our design graph. Right? Some of the things that can be learned would be classes of parts, the co-occurrence relationships between these part classes, and potentially at an even higher level, learning some of the functional relationships. Right? So learning about pistons, arms, cams, and gears, when you put them together, you get the basis for an engine. All right, so to quickly summarize there, we've built out a graph, a design graph, by first focusing on the designs and the embedded parts, and then learning the part-to-part relationships and the design-to-design relationships and all those permutations. Right? So even at this bedrock level, the design graph that we're able to create is quite interesting, and it enables these navigate, explore, and discover workflows that are resonating with some of the customers that we've been showing this to. All right, so given that parts are like our words, I guess the next task is kind of figure out, well, how do we identify these parts? How do we actually build out our part dictionary so we can start building out the graph? All right, so the ideal scenario would be as you pull out these parts from the design files, they come with metadata, with lots of textual information. Right? Things like the name, maybe some very nice descriptions of how it's being used. Now, unfortunately, this is not very reliable data. Right? For the most case, it's missing data. And in the cases when you do have the data, it has a lot of garbage in there as well. Right? So there is rich little nuggets in there, but it's not something that we can rely on. We could look at part numbers. But again, unfortunately, there's no universal part numbering standard. All right? So again, you get all kinds of scatter there. You may even have companies coming up with their own naming schemes. Sometimes it's even just a hash. All right? So again, not very reliable. In this day of 3D printing and custom parts or bespoke parts, right, you now have these parts that don't have very meaningful tags at all. Right? But again, because we are dealing in this 3D design space, there is something that we can rely on, and that's the shape. As we extract out the parts from these design files, they have the exact 3D shape that you're going to expect when you're manufacturing them or putting things together. All right? So it turns out shape is very reliable. It's always going to be there, and it's very rich in information. Okay, there's challenges, though. All right? So with shape, you need to consider both local features and global features. All right? So with those Lego pieces on the left, really those local features, the nub connectors, that's really the important feature for identifying Lego parts. But in the case of chairs, it's really the global structure, all right? The global feature of the legs and the platform and the backing that identifies chairs. Right? Some other things that we have to consider are things like transform and tessellation invariants. All right? As we extract these parts out of the design files, all right, it shouldn't matter how they're positioned or oriented or scaled or how they've been tessellated. Right? If it has the same shape, when we extract them out, they should have the same identifier. All right, so to that end, we have two kinds of shape descriptors for our parts. The first one is a global descriptor. It's called the Spherical Harmonic Shape Descriptor, and it was something that was developed out of Princeton in the mid-2000s. The basic idea there is you take these concentric spheres and then compute the spherical harmonics where those spheres intersect the shape. You take the norm of the harmonics, add them up, and you get this transform invariant descriptor. Right? To get local features, we look at the vertices that make up your part. All right? And we try to characterize the local shape around those vertices. We find that actually if we look at pairs of vertices and their local shape, we get a very nice local descriptor, hence the name bigram shape descriptor. Right, so to deal with the tessellation invariants, we do a lot of mesh cleanup and processing. And one of the things that we do is we try to standardize the mesh, take out all the redundant triangles in a given shape and try to reduce it kind of to its minimum set. So we use something called a modified Q-slim algorithm to do that. Right, and we should just note that as we're reducing those triangles to sort of the minimum set, we also maintain the original shape of the part. All right, so after a lot of experimentation, research, and building up these various pieces, we've come up with a system that can mine the design files, come up with these part dictionaries, and then start learning some of these part classes. All right, so we can automatically detect things like gears, springs, stairs, and so on. And we also do some very simple labeling to get these part classes as well. We can also do some very rudimentary design clustering using a bag of parts model. All right, so moving on to pipelines here. So end of last year, after a lot of blood, sweat, tears, spit, glue, whatever, we were able to cobble together an end-to-end pipeline, right, to generate this design graph. We could crawl our storage systems, do the mesh cleanup, the learning, and generate that graph. Right? We can then take the materialized view of that graph and push it into a query-optimized graph database using a custom Redis cluster. We added text indexing so we could search into the graph. We added a front-end API server so that we could query into the graph and pull out associated part data. Right? And then we built two prototype interfaces based off this idea of navigate, explore, and discover. And we came away quite encouraged, right? We got good customer response in terms of the experience. So yeah, end of the year, we're pretty happy in terms of the design graph work and how it was going to play out in terms of features for our customers, right? The big problem, though, or the big pain that we were experiencing, though, was the pipeline itself, all right? It was a customized, distributed pipeline that was incredibly painful to run and maintain, all right? It was painful to run and keep track of multiple experiments on that pipeline. And it was very difficult to incorporate new ideas into our pipeline. Right? Our data scientist, he worked in Python, NumPy, SciPy, some of his own cleaned up data sets. When he came up with ideas that we wanted to put into the pipeline, it was this very bug-ridden, tedious porting effort to go from Python to our pipeline, which was this hybrid mix of Go and C++. Right? So as you can imagine, beginning of this year, we said, OK, we got to redo this pipeline because this isn't going to scale. So quickly, we honed in on Spark, as you can imagine. Right? So Spark, with its in-memory efficient processing, the elegant RDD abstraction, the vibrant community, the Python support, it was really a no-brainer for us to move to Spark. Basically port our old pipeline onto Spark. Our challenge, though, was that we really rely on a lot of C++. Okay, as I've mentioned in sort of the lead up to here, we do a lot of mesh processing and cleanup, and those depend on well-tested C++ libraries. All right, so we didn't want to mess around with JNI and trying to deal with all that kind of complexity. So we kind of went with this simplified approach where we said, let's go back to the old pipeline, take out all those data transforms, and let's clean them up and isolate them into these simple little applications, all right? Simple little data transform applications that take data in and data out, right? So for example, it might take a part as data in, process it, clean up the mesh into some standardized form, all right? So we did that. We kind of broke it up into these very simple, specific external executables that were dependent on C++. And then we wrapped it with Python code so that we could then call them from within an RDD transform. Right? So for example, you could take an RDD referencing a number of parts, do an RDD transform, in this example, probably a map, where we then clean up those parts and get an output RDD with the cleaned up meshes, right? But we have to also deal with errors, right? Our external applications may crash because of bugs, but more likely they might crash because they ran out of memory, right? We tend to run our cluster. We stress them out quite a bit by running a lot of Spark workers per core, right? So especially in the initial runnings of the pipeline, you'll have situations where the instances are running and processing some heavy meshes and perhaps running out of resources, hence the crash. Right? We also have failure conditions where maybe the external application needs to go and fetch some data from the network or save some results to the network, and on those failures, we want to handle those as well. All right, so to this wrapper, we added error handling code where we'd look at the exit status of the application and then tag the items in the RDD accordingly. All right? If it succeeded, it would be tagged as completed. If it failed, it would be tagged as failed. All right, so once the RDD has been processed, we then filter into it, and if we find any failures, we actually take that RDD back to the beginning and run it through that stage again. Right? Now, items that have successfully completed will pass through, and we only reprocess the ones that failed. And we do that over and over again until either all the items have been successfully transformed or we hit some circuit breaking count, at which point we then take the problematic items out, put them into some debug bin, take the successful items, package them up into an RDD, which we then pass on to the next stage of the pipeline. Right? So this worked out really nicely for us. We were able to take the old pipeline and make it run on a Sparkified pipeline. Right? This is just kind of a little aside. Because we've taken those external applications, it allowed us to really isolate the tests, which allowed us to more quickly get to a robust state with our pipeline. So for example, meshes that were crashing the system, we could just throw them into these isolated tests and get things working nice and cleanly. All right, so just quick summary here. We took the old pipeline, broke it up into the simplified, specific data in, data out, transform applications. We wrote a Python module on top of Spark. It was actually very light, that would handle calling out to these applications and deal with things like errors or retries to ensure that we're able to process our data accordingly. All right, so to deal or address the issue we had with running and tracking multiple experiments, we added persistent lineage to our pipeline. All right, so what happens here is that we checkpoint RDDs at various points along the pipeline in an immutable store, all right? And then we also add some metadata to those checkpoint data so that we can track its lineage, all right? So for any output RDD, we know exactly what its input RDDs were, plus any parameters that we needed during that cleanup step, all right? So the consequence of that is that we could run the pipeline multiple times and always know how that data got generated, right? And also because of the immutable store, we also knew that running the pipeline multiple times, we'd never be stomping on top of previous results, right? And this allowed us to have multiple people working on that pipeline, running their experiments, and know that they're not getting messed by someone else, right? And then finally, we found that this also lent itself very nicely to getting new ideas into the pipeline. Right? Again, our data scientist works in Python, but this time now working in PySpark, he could run his experiments, use the checkpointed data so that we're all dealing with the same data formats. At the point that he felt comfortable that he wanted to see this in the full pipeline, we could literally just drop that into the pipeline, into the Spark application itself. So that worked out very nicely for us. All right, so let me see if this will work. Okay, so I'm going to give you a quick demo. This is a smaller test set that I'll be exploring, but I just want to give you a flavor of this navigate, explore, and discover workflow that I've been mentioning. All right, so here I first do a text search into our design file corpus, all right, looking for files that have house in them. All right, so nothing special there, but if I select one of those files, right, we're actually now going to the design graph. And from that graph, we're pulling in any associated data. right? So in this panel over here, the lower right one, we're seeing all the canonical parts that went into the design of that house. If we look in the panel above it, we see all the part groups that went into it with some auto labeling. All right? So this is kind of a nice bill of materials, if you will. Now, because this is a graph, we can actually start exploring things. All right? So by double-clicking on one of those part groups, this one has to do with level-bearing walls. All right? We're actually pivoting into the graph, right? And looking at that specific part group, we see the canonical parts that go into that group. We see all the design files that have that part group in it, as well as the various design groups. All right, so let's see. Now, because we use a lot of shape analysis in our system, we can also do things like shape similarity queries. We can go back to the graph and pull in all the parts that are associated with a particular shape. Right? So here we're looking at a single basin sink. All right? So we can look at some of the similar shapes that we pulled out of the graph. Right? And as I select them, you can see the design files that those particular parts are appearing in. All right? We can even go directly back to the design file source to see that part in full context. Or not. Oh, there we go. All right, so you can see that particular part in the design file. All right, so that's just a quick demo of that navigate, explore workflow. All right, so let me just quickly finish up here. In terms of next steps, right now we process the data in a batch manner. We're starting to look at stream processing. All right, I think it'll simplify some of our error handling where items that fail we can just throw back into the queue. But more importantly, we're looking at pipelining some of the more time-consuming parts, the mesh cleanup in our system. All right. This also helps us move towards incremental updates of the design graph, kind of along the Lambda architecture idea, where we can incrementally consume design files, run the parts against a classifier, and incrementally update the design graph. And then perhaps periodically, weekly, monthly, or whatever, do an exhaustive update of the graph so that we have a robust representation. All right, so with that, let me just acknowledge the design graph team led by Mike Haley. We have Senthil, Tara, Kwa, Federico, Morgan, Carlos, and Santiago. And of course, I'd like to thank the Spark team and the community for creating this fantastic platform. For us, it's really allowed us to focus on the design graph problem and not so much a lot of the distributed framework headaches. All right, so thank you very much.
So do we have questions?
All right, thank you.
Well, thank you, Yotto.
Sure.
That was a great talk. I was a mechanical engineer in undergrad, and I used AutoCAD several times.
Awesome.
It's great to see what's happening behind the scenes.
Cool.
Yeah.